Welcome to Wireless Future. I'm Eric Larsson, and I'm here as always with Emil Björnsson. Emil, good morning. How are you today?
I'm fine. It's finally spring in Stockholm. How are you today?
I'm good, thank you. I spent the entire weekend looking forward to recording this podcast with you and with our guest today, Angel Lozano, professor at UPF in Spain, IEEE fellow, a pioneer of MIMO communications theory, and also an author of two impactful papers. Is the Physical Layer Dead in 2011, and then the award-winning What Will 5G Be in 2014. Hello, Angel. How are you this morning?
Good morning, Eric. Good morning, Emil. And thanks for inviting me. I'm a big fan of this podcast, so it's an honor to be part of it today. Somehow, no one in our community had thought about using a platform of this sort to disseminate ideas, even though this is a preferred platform for young people. So kudos to you guys on this initiative.
Well, thanks a lot. I mean, it's great to have you here with us today. And the format is going to be that we have a conversation with you. And I guess Emily and I will do our best to ask provocative questions. So let's get started. So I guess what I'd like to start off here is to talk a few minutes about 5G and the predictions that you made in your 2014 paper. So did 5G evolve and become what you envisioned? Or is it too early to tell even? I mean, for example, it seems that millimeter wave communication has not really taken off the way that lots of folks imagined. What do you think of all this?
There is this thing with the wireless generations that when we are at generation G, we tend to downplay it and we hype up the next generation, generation G plus 1. And we say that that will be the true revolution. And then once we get to generation G plus 1, we immediately downplay it and we start pedaling generation G plus 2, and so on and so forth, right? That's already happening with 5G. There's people out there saying that, all the odd number generations have been a fiasco, and we're going to need 6G to fix everything that's wrong with 5G. So it's a wheel that keeps turning and turning around. With 4G initially, there was an attempt to break with that. And in fact, the name long-term evolution was coined to signify that this was a standard that could be improved and revised indefinitely, right? Without the need for new generation numbers. But in the end, the pressure to bring to market a new brand was too strong. So we had that 3GPP release 14 was still 4G, and then release 15 was 5G. And it could have been, 4G plus rather than 5G, but instead it was 5G from that point on. But anyway, getting at your question, I do not think that 5G is very revolutionary in terms of the physical layer. I would say in terms of the physical layer, 2G or 4G were much more disruptive, right? 2G brought about digitalization, and 4G brought the mobile internet. 5G is 4G with more bandwidth, more antennas, shorter frames, and with a bunch of cute things like this integrated access and backhaul. And of course, with the novelty of breaking through the 6 gigahertz ceiling into this brand new world of the millimeter waves, where the channel is rather different than we are used to. Now, I do think that 5G is a very interesting proposition in other ways. For instance, in how it has grown beyond being a network that provides just mobile broadband access. So it also subsumes IoT and other types of access. So thanks to its flexible frame structure and this nice slicing feature, it ends up being a platform on which an operator can define different types of virtual networks customized to different needs and different types of access. So with 5G, an operator can do what before might have required several physical access networks, and that's neat. And then another interesting aspect of 5G, perhaps the most disruptive one to me, is that in its design, it implicitly declares that the smartphone is no longer the center of the wireless universe, right? 5G, of course, still intends to provide connectivity to smartphones, but that's not the only thing it intends to do, perhaps not even the most important one. A key driver for 5G, in fact, have been all the verticals for the various industries, especially in automotive. I remember some years ago, we used to say that a car was a computer with wheels, and now it's a smartphone with wheels. So here's what I think the real disruption may be for 5G, in how it shakes up the existing wireless ecosystem. For instance, it's the first time that spectrum is being auctioned for use by private enterprises rather than by operators. So you may have, say, I don't know, Siemens running its own private network in its factories without an operator. And this moves things in the direction of the vision that Google laid down years ago of a future without operators, or at least without operators in the way that we understand them today. It'll be fascinating to see how that pans out. And in terms of the physical layer, as you were saying, it'll be interesting to track down what happens with the millimeter wave deployments. Apparently, the propagation is better than anticipated by many people, with substantial coverage even in non-line of sight conditions. But there are still issues with power consumption, beamforming, etc. So I think the jury is still out on the performance. Whatever happens, though, I do think that Ted Rappaport is right when he says that all of this millimeter wave activity is positive by itself in terms of how it's accelerating the development of RF circuitry, much in the same way that CDMA had a tremendous impact on the development of baseband signal processors, even if the CDMA concept itself faded away.
Mm-hmm. Yeah, these are interesting perspectives. I mean, I guess I tended to think that the big deal with 5G was that we finally had a wireless standard that included reciprocity-based multi-user MIMO beamforming, truly, I mean, through the use of large or massive antenna arrays. Or what do you say, Emil?
Yeah, I've been thinking that if one of the main things, even if we like to talk about all the fancy applications, if the main driver for developing technologies is that the traffic is just growing, so we need to have a new way of multiplexing them, then if the conventional way of multiplexing have been to deploy more base stations or having more spectrum, now we're also using the spatial domain with MIMO technology to do as part of the multiplexing. Okay, so maybe we should move on and continue our discussion. I had some questions. I like this paper, Is the Physical Layer Dead? But I also have the impression that this is a paper that is often misunderstood from the perspective that people are nowadays reading the title and they think, oh, this guy were thinking that there won't be any changes to the physical layer. And then massive MIMO and millimeter wave came around. But then if you actually go in and look into the paper, you get the impression that that isn't at all the point you're saying. Could you summarize what is the main point you want to make with that paper?
Yeah, that paper was a really fun project. We started with a roundtable we had at some conference, the same bunch of people. The mastermind was Misha Dollar, who is now at King's College, London. But back then, he was a neighbor of mine here in Barcelona, physical neighbor. We walking distance from home. And he had the idea for the roundtable. And in fact, you're right. The title we had for the roundtable was not formulated as a question, but as a statement. It was, the physical layer is dead, exclamation point. And, Misha thought that would draw a bigger audience, and it did. We had a huge turnout. And after the event, various people approached us and explained that they had really enjoyed it and that we should write about it, and so we did. But for the paper, we changed the statement into a question, and we gave it a more upbeat, positive tone. All of us still work on physical layer stuff, so it certainly wasn't dead. But I do think that the physical layer has seen better days. So if you want to humor me for 5 minutes as we do a quick exercise and think about the core ideas in 5G, right? And let me say beforehand that there is amazing engineering in 5G. Amazing. I had the good fortune of attending 3GPP meetings in a previous lifetime, and it's a very humbling experience. I mean, to see so many outstanding engineers at work designing these super complicated systems. But let's think about the ideas from a research standpoint. Let's see, the 5G waveforms are OFDM, okay, a concept that has its roots in the 1960s. This guy, Robert Chang at Bell Labs, published the first paper on multi-carrier transmission, I think in 1965. Then we have LDPC codes, invented by Gallagher at MIT, also in the 60s. Then Massive MIMO, which is MIMO on steroids. And MIMO dates at least back to the 90s, arguably even to the 1980s. Millimeter wave is even older, almost dating back to Marconi. There's this Indian fellow, Bose, who was transmitting at 60 gigahertz by the turn of the 20th century. Then we have cell cooperation, an idea clearly traceable back to Aaron Weiner in the 90s, again at Bell Labs. I guess we could regard unlicensed spectrum as an ingredient of 5G, and that would go back to the 80s. Then virtualization, things like Cloud RAN are a modern embodiment of this old dream of software-defined radios, again a 1980s idea. And don't get me started with NOMA, which is a prime example of taking an existing idea and giving it a new name so it can seem like we're doing something new. So NOMA is just good old superposition coding, right? A textbook idea from the 70s. One just has to pick up the Thomas and Copper classic textbook and it's all there, right? There is one idea in 5G that is truly original, and that's the polar coding technique. Original meaning recent, right? This is a result of a single guy locking himself in his office for a couple of years, away from the world, and then coming out with something very original. And in this age of frantic activity, when we're all running around with our tongue out, there's a message there that perhaps what we need to do, at least every once in a while, is to withdraw and let our mind run free without the influence of what everybody else is doing. Right? Maybe. At least it worked for him. Now, at the same time, we do have to accept that we are in a mature discipline. So explosively new results are going to be more infrequent than they used to. I have this unproven theorem that the more mature a discipline, the longer the titles of the papers. So years ago, our titles would be, would have been, multi-carrier transmission, or I don't know, on the CDMA capacity, right? And these days, the typical title in the transactions will be something like, I don't know, device to device, energy efficient, multicast, first scheduling for small scale cell millimeter wave communication, right? So we try to squeeze a bit of novelty out of combining a whole bunch of known things. Anyway, I'm getting off topic. So coming back to the physical layer is dead paper, another of the interesting arguments in there was the objection to the way some people pick their models and their assumptions. Apparently not thinking much about them, because you often see results that are direct artifacts of the assumptions rather than genuine insight. You go through the paper, you see the assumption, you already can anticipate what the conclusion is going to be based on the model, right? And then there was this issue of the interaction between industry and academia, which I think is also relevant. In the golden decades of the last century, many of the powerful ideas emerged at Bell Labs, which was not a university, but it was the research arm of a corporation. So there were people in there who could keep researchers honest and grounded, right? Now, the vast majority of published work comes from academia, and this interaction doesn't come so naturally. Most faculty members have never set foot in the industry, and that doesn't help. And as we wrote in the paper, frontier research must be unhindered, definitely. If you're the guy first coming up with MIMO, you're entitled to consider a very idealized channel, perfect channel estimation, etc., right? You're just trying to figure out if the idea is even feasible and what its potential is. But if 30 years later, you're the guy writing paper number 5,000 on MIMO, proposing some new precoder that squeezes another half dB of gain, you do have to worry about the channel model and everything else, because your half dB is not credible otherwise. So here, having someone from industry that you can discuss with, it's a big plus, I think.
So do you think this situation with that academia and industry are sort of running away from each other, have that become better during the last 10 years since you wrote this paper, or is it still the same issue as you were identifying that time?
Yeah, I'm not sure. I'm not sure much had changed in the last 10 years. I think there's a subset of academics that interact with industry, but it's a small subset. And it is certainly possible for academics who don't work at all with industry to make a great contribution that makes its way into standards and products. And we just saw the example of Arican with the Ponger codes. But in my opinion, that works for very basic or fundamental contributions, right? For research that is not of a very fundamental nature, it helps to be anchored in the real world. And to me, at least, socializing with people from industry is the easiest way to go about this. I'm sure it's not the only way, but it's the easiest and the one that has worked the best for me.
So, I mean, I think in your 2011 paper, you talked about also lots of folks in academia being lost in asymptotics. And if we take as an example the development of massive MIMO and its underpinning theory, do you think that academia contributed there, or was it mostly industry? Were we too lost in asymptotics?
It's a great question. So I think that the roots of massive MIMO ran pretty deep. In the 1990s, AT&T was thinking about expanding their fixed wireless access service in the eastern US. So they asked Bell Labs for ideas. And what emerged was something that coincidentally carried my name, Project Angel. It was a TDD system of macro cells where the base stations had these very large antenna arrays to form pencil beams using beamforming in the downlink, in the uplink, conjugate beamforming in the downlink. The antenna spacing was very tight, and the arrays were on these very high towers above the clutter. So the propagation was highly directional, often line of sight. But other than that, they almost had massive MIMO, okay? Almost. Except they never thought they could multiplex more than one beam at the same time, right? And on the same frequency. This key insight that you could spatially multiplex multiple beams was only then starting to emerge. And in this project, they never thought about it. Instead, they got tangled up trying to coordinate the beams of different base stations. And the whole thing became very complicated and so expensive that the business case fell apart and AT&T abandoned the idea. And funny enough, a guy in the very same building in New Jersey, Jerry Foschini, was just about then coming up with something that would be called BLAST, and which was an embodiment of MIMO. In my book with Robert Heath, we have a historical section that we put together based on conversations with all the key players. So we talked to Jack Winters, Foschini, Paul Rush, Stenlatar, etc. So if anyone is interested in how MIMO came to be, I think they may enjoy that section. I think we present a pretty unbiased perspective. Now, in terms of massive MIMO in the way we understand it now, I think that a tremendous amount of credit must go to Tom Marzetta. He spent years waving the flag of massive MIMO, even before he had that name. And by the way, I think it's a name that Tom doesn't much care for. And no one in his own company, Alcatel-Lucent at the time, was paying much attention. It wasn't until competing companies, especially Samsung, picked up the idea and renamed it full dimension MIMO, that things starting to happen. And you guys up there in Linköping, you guys were, to the best of my knowledge, the first academics to jump on it. So I think you also deserve a lot of credit for disseminating the idea within academia and for coming up with some of the important early results. Now, let me get to the second part of your question. this idea of asymptopia. This is something that Robert Heath came up with. If I remember correctly, I don't have the paper here, but I think what we said is that when you're in asymptopia, you have to proceed with caution. Okay? It's important to realize that asymptotic results are not equally relevant in all regimes and in all channels. There is a delicious paper by Echevilleri entitled "How Far is Infinity?" that discusses that point and gives some examples. There are cases where 10 antennas are essentially as good as infinite. And in other cases, it may take hundreds of antennas for some asymptotic behavior to take hold. In the case of massive MIMO, it's just the law of large numbers that is at play. And my impression is that everything is pretty safe, even with very few antennas. So yeah, I wouldn't worry about that. The only aspect in which I think the asymptotic analysis in Tom's paper was misinterpreted by many people is in how, by letting the number of antennas per base station go truly to infinity, it portrayed pilot contamination as this really important effect, this really important limitation, because in that limit, everything else, fading, noise, interference, everything completely disappears, right? And all you're left with is pilot contamination. That's the only thing keeping you from having infinite capacity, right? Mm. But in reality, once you back off just a bit from having infinitely many antennas, just a bit, you have many antennas but finite, pilot contamination becomes negligible next to the residual interference that you have. But I think people didn't bother checking this. So we had hundreds of papers addressing a problem that isn't really a problem to begin with.
Yeah, that's such an important point. I mean, and of course you're entirely right that pilot contamination is an important impairment, but it can be done away with rather easily. I mean, for example, through appropriate pilot reuse and planning. So on this point on asymptotics, I think the way to think about asymptotics is as a way of justifying an approximation, right? And then the question is, what does approximation mean? Well, to a mathematician, any real number is approximately equal to 0, or to 1 for that matter. So certainly, but then I think at the same time it's also important to stress the fact that, let's say, modern massive MIMO analysis techniques do not rely on asymptotics in any way. In fact, the massive MIMO results, for example, that we have in the fundamentals book, these are rigorous lower bounds on the ergodic capacity, right? So there is no asymptotics involved whatsoever. And I think this is a point that obviously I've made many times before, and Emil also, and probably you as well, Angel. But it is a point which is worth reiterating. And it also serves to amplify the point that, well, massive MIMO by all means is a highly useful transmission technology, right? But it is also, in my view, a way of teaching physical layer wireless communications, just by the sheer beauty and elegance of the capacity expressions and the optimization, the power control formulations, for example, that result from this theory. All right, good. Emil.
Yeah, no, I think that there is definitely a case for us being lost in asymptopia for the sort of the case when you submitted a paper, people saying, well, if you're not studying M goes to infinity, where M is number of antennas, then it's not a massive MIMO paper. That's something I heard many times from reviewers. And also the kind of focus on, if you can't find a closed form expression, so you're not selecting the right or maybe the wrong, processing the wrong channel models so that you get a nice formula from which you can study nicely the asymptotics, well, then you are using the wrong models. Or maybe it's the other way around, that you are overly simplifying reality. Anyway, so one question I often get is what comes after massive MIMO? Will, like, every technology now, 6G and so on, build on using large arrays of antennas, or is there anything else we can do beyond that?
Yeah, let's see. I think that we recognized long ago that the cell is an artificial limitation, right? So it's something that made sense years ago, but perhaps not anymore. Because, I mean, cells are a completely artificial construct, right? There are no lines on the ground saying, okay, this is the end of the cell, here starts the next cell. There are no cells, they're only base stations. And there's no reason why users should connect to only one base station, right? So cell-free, and you guys are the champions of cell-free, and it makes sense. But I think that's one aspect of something broader and more bigger moving forward, which is CRAN. So I see CRAN as a truly new paradigm. And let me note that the C in CRAN need not stand for cloud, meaning, cloud would mean general purpose computing, right? The C could stand just for centralized, meaning that it could still require specialized hardware. But either way, CRAN, I think, really breaks off with the structure that radio access networks have had in the past. Because now we're taking this key ingredient that is the base station, and we are deconstructing it, right? There has been a gradual process where we've gone from the base station as a strictly physical entity to the node B as a more virtual concept where the antennas are perhaps somewhat distributed, right? And maybe separate from the baseband processing. But still, the node B is a distinct separate entity, right? And then with CRAN, we'll be taking the baseband processing for all the node Bs and gathering them together in one place. And this opens the door to many new possibilities. Among them, everything having to do with cell-free, because I think the true potential of cell-free emerges when you can really harness the interference. And you cannot really do that in a distributed fashion. To upgrade your CRAN to 6G or 7G when the time comes, we won't have to send a technician to every base station to replace hardware. We'll only need to replace stuff in the central sites, right? And if we ever truly manage to softwareize everything, then changing to 6G or 7G is going to be like upgrading the operating system on your computer. So this new paradigm of CRAN, I think, will have been made possible by decades of Moore's law in terms of processing power and by similar improvements in backhaul. I remember 20 years ago, the backhaul was made up of T1 lines carrying 1.5 megabits per second. And today, an enhanced CPRI line carries 10 gigabits per second. So that's 4 orders of magnitude in 20 years. So we had Moore's law for the processing and then something similar to Moore's law for the backhaul. And it's just the raw power of technology that makes something like CRAN possible. And when you see it in action, it's impressive. It really, I do think that this is the future, at least for ultra-dense deployments, CRAN.
Yeah, I think you're pointing out something important here also, which connects to what you said earlier with some of the 5G enabling technological components are things that were invented much earlier, but now it's sort of the time to utilize them. And with decentralized kind of processing, it's also things like coordinated multipoint that people talked a lot about 10 years ago, but didn't really take off within 4G. But now with the CRAN architecture, we can all of a sudden do it and start to evolve this kind of ideas into the cell-free network structure. Eric?
Yeah, interesting. I mean, so one question that I've been sitting on is, where are the true limitations of wireless communications? I've always argued that the physics is what limits us, right? I mean, the fact that the speed of light is finite, for example, puts limits on how long the coherence time is, and therefore on how much time we have to obtain channel state information, and which in turn gives us or limits the number of users that we can multiplex spatially and all that. Do you agree with this, or are there other limiting factors? I mean, how about, for example, processing in digital hardware, or limitations on like the MAC layer with buffers and other things that are placed there?
No, I absolutely agree with you. My former boss at Benelux, Reinaldo Valenzuela, always told us that we should think big and then limit it only by the laws of physics and by information theory. Now, I do think that the laws of physics have to be interpreted in a broad fashion. For instance, the limitations of computational complexity or the power constraints are physical limitations, right?
Yeah, I guess energy consumption is one factor here, right? Which is very closely tied also to the physics.
Absolutely. One cannot propose, say, a handheld device operating at terahertz frequencies on bandwidths of 20 gigahertz with full resolution digital conversion because just the ADC is going to consume 6 or 7 watts. And that's fundamental. It's not that in a few years we'll have better ADCs, reducing that to milliwatts. There is a minimum amount of power that is required to compare against a threshold. And modern ADCs are not far from that already. So this is not a practical limitation that can be ignored. It's a fundamental limitation implied by the laws of physics, and it's not going to go away. So if your receiver had better work with low resolution ADCs, or else it's going to melt the hand of the user.
That's an important thing, I mean, with the ADCs. In fact, I didn't know that they were so close to the physical limits there, because, I mean, if we think of electronics and digital computing in general, then we've been rather far from the physical limits, and we are still far from the physical limits, right? And I mean, the amazing development of the microelectronics over the last decades have shown that with all clarity, I think. So the physics is really what sets the boundaries here of what's possible, right? I mean, again, the speed of light as a fundamental limiting factor that we just simply can't change. And then obviously the wave equation and the laws of conservation of energy and so forth. It seems like we agree on this point. I don't know, Emil, if you also agree.
Yeah, no, I don't think we will change the air into some other material that is increasing the speed of light that would have other...
Well, it's not gonna help much, right? I mean, the speed of light is what it is.
I guess it depends on what medium you have, but in any case, it will probably just reduce the...
you could reduce it, I mean, but we can't increase it, right? No. So, and that's the problem, because the speed of light, one more time, dictates for how long time the channel is coherent, which in turn dictates how many pilot symbols that we can cram into a channel coherence block, which in turn dictates how many channels that we can learn how many terminals or users that we can learn the channel to, right? Which determines how many users we could ever meaningfully multiplex using an antenna array, be it massive MIMO, be it CRAN or cell-free, or whatever other technology you could think of. But the limit is the coherence and therefore the speed of light. Very good. So
if we think on just a basic setup with a single link from one transmitter to one receiver, in this 2011 paper, Is a Physical Layer Dead, you were arguing that, when it comes to the standard analysis there, most things were already known, so there is no big point for academia to continue looking into those details because, there's not much to improve. But then you were mentioning that shorter codes, if you're not at the capacity achieving scenarios or using polar codes or looking into hardware impairments and their impact on the channel capacity were important future directions. If you look at these kind of questions today, do you think that we have addressed those things during the last 10 years?
Yeah, it was pleasing that we published that paper in 2011. And I think just about a year later, there was this big bang on short block length communication with the seminal work by Yuri Polyansky and company. And then one of the issues that gave momentum to 5G was the ultra-reliable low-latency communication, which is a big challenge because really here we're up against a kind of uncertainty principle, right? It's easy to do reliable communication with high latency, and it's easy to do low latency communication if you don't care about the error rate, right? But it's hard to be both low latency and reliable at the same time. I haven't done any work in this space, but I'm tracking the progress that people are making with a lot of interest. But besides this issue of the low latency, the glass of the single link communication is half full and half empty. So on the one hand, we're still several dB away from capacity when operating a single link. So it would seem that there is room for improvement, right? But then when you dissect these several dB, as for instance, people like Markus Rupp have done, you find that 1 dB comes from the QAM constellation not being optimally shaped. Another dB comes from the coding block length being finite. Another dB is due to the channel coherence, with Eric was just talking about, which is fundamental. Another dB is from imperfect sampling timings, etc. It's possible that we can still shave a few tens of dB here and there, but would you recommend the student starting his or her PhD to work on this? Probably not.
Yeah, no, I think this is an important point as well, that maybe those things that are left there are so closely tied to implementation things that you need to be strongly connected to the industry to know what the actual state of the art is in order to do anything work, and then your research will probably be very hard to publish anyway, because the reviewers unfortunately are not familiar with all those details either. So I wouldn't recommend students working into those type of things as well.
Mm-hmm. Yeah, perhaps. I mean, you're arguing essentially that systems, or even like a point-to-point communication link, is made up of so many different components, and each component operates by a bit away from the corresponding theoretical limit. And now the gap to the theoretical limit, these gaps, they add up because we have so many components. If we were to really gain substantially in the end, we would have to shave off from that gap in each one of the components. That's certainly agreeable, but it in itself, I think, does not exclude the possibility that it might be some completely radical approach to link design, right? I mean, rather than modulation and coding and sampling and all that, there might be something else that we just haven't discovered yet, and which brings us closest these dBs that we were talking about. Who knows? Anyways, so how about 6G? There are, I think, currently lots of discussions about what 6G will be and how it will be designed. And one tool that has been, if not emerged recently, but at least which has been recently advocated a lot for the design even of wireless links and systems, is machine learning, right? I mean, the other week or month, I read a paper where they argued for AI, artificial intelligence for air interface design. So we'd like to hear your views on this. Where is 6G heading? And is machine learning going to be something like a fundamental enabler for 6G? Or what do you think, Angel?
Yeah, that's a clever term, eh? AI for AI, I like it. Well, certainly it's impossible to discuss what may come in wireless or in any other field without discussing machine learning. I mean, how could we, right? More than a discipline, it's become a religion. And everybody wonders whether they should convert or not. I mean, the truth is that as engineers, we cannot ignore something that works. And so it makes good sense that we incorporate it as another weapon in our arsenal. But that doesn't mean we should throw away everything we already have, right? Especially tools and techniques that have served us very well for years. I think that machine learning should augment, not replace, what we have. And the main question to me is, when we give up on solving a problem in, say, the conventional way, right, and we throw machine learning at it, what kind of insights are we giving up? Because machine learning, for all its might, doesn't illuminate problems. It doesn't reveal what the solution is. It just sort of spits it out. In fact, it spits out an approximation to the solution. So, as some savvy people have said, machine learning is great for problems where we already understand the mechanisms that are at play, so we're not desperate for insight. But these mechanisms are just inherently complicated and impossible to model, right? I think a good example in our field is channel modeling. We know that the mechanism at play is Maxwell's equations. but they're just unwieldy in the real world. In fact, it's remarkable that we were able to design various generations of systems, 1G, 2G mostly, on the back of very simple models with just a handful of parameters, path mouse exponent, intercept, shadow fading, standard deviation. That was pretty much it, right? And it was wonderful how one could draw great intuition on the impact of each of these parameters on interference, capacity, etc. But since 3G, systems have indeed become much more complex, more heterogeneous, and the intricacy of channel models has exploded. If you look at the current 3GPP special channel model, it's just insanely parameterized. So perhaps it's better to just directly use a generative model trained on measured channel samples for whatever environment we desire, right? We could have a standardized data set for each type of environment, and then we could benchmark our solutions using generative models trained on these data sets, right? It wouldn't be any more obscure than the current 3GPP models, and it would be more precise. I'm sure we could come up with a whole bunch of other problems besides channel modeling, say resource provisioning, right? Anything that depends on what the users are doing, because modeling the behavior of users is notoriously difficult, as difficult as modeling the behavior of the channel itself. But I sort of reject the idea of sort of blanket applying machine learning to everything, right? Even to problems for which you already have good solutions. There is this anecdote of a recent paper using machine learning to rediscover QPSK. And apparently it's not a joke. There are people who defend applying machine learning to things like modulation, coding, or channel estimation on the argument of robustness against, I don't know, say, nonlinear behaviors in the amplifiers, right? And I'm sure that indeed the machine learning, the modulator, could learn from data how to compensate for these nonlinear behaviors. But then we're giving up on understanding the inner workings of all of this, right? And what good solutions are like and why. So I'd rather try dissecting all of that. And it could well be that once we understand what's going on, the best implementation is a data-driven one. Yes, that is, of course, possible.
Yeah, you were mentioning these few dBs that are left in the single link performance. Could we reach better there by taking what we know and throw machine learning on top of that and try to squeeze out those last bits of information?
Yeah, for instance, right, we know that 1.5 dB is because the QAM constellations don't have the optimum shape, right? And if you apply machine learning, it's going to design constellations that are circular, that have unequal probabilities, right? That look more Gaussian than a QAM, and that's going to cut off at least fraction of that 1.5 dB, right? But we can do that, conventionally, right? We know what the optimum shape is for a constellation. It has to be as Gaussian as possible, right? We haven't bothered. We've been using QAMs, even though we know they're suboptimal. So in this case, we don't need machine learning. We can design constellations that have weird shapes and that are going to do a little better, right?
Yeah, and that was, in fact, one of the points I was also sitting on. I mean, quite a long time ago, there used to be papers on constellation design and shaping, right? So in a way, it's like, all right, we're using machine learning now to revive and bring back some of the things that we knew until 15 years ago. Okay.
Yeah, I remember there were like a book on 5G waveforms listing 10 different options. Then we anyway picked more or less the same one as we had in 4G. Not because it was the best option, but rather that it was sort of the known one that was engineering-wise the one that made most sense to continue with. So if we have a look at some of the things that people are researching now under the 6G umbrella, one thing that we talked previously about in this podcast is reconfigurable intelligent surface or intelligent reflecting surfaces, whatever you want to call them. Do you think this is a technology that will be utilized ever to a large extent? And will it in that case happen during 6 years? Is something that will happen much further into the future? I mean, are we waiting for Apple to release the eye wallpaper that everyone will cover the home with, and then all of a sudden it just works? You just have perfect coverage everywhere.
Well, yeah, there's a lot of excitement about this right now, and I can understand why. I have mixed feelings about it. There are days when I think, wow, this is a paradigm change. We finally go from being at the mercy of the channel to controlling what the channel is doing, at least to some extent, right? And that's something to get excited about. But then other times I think it's just a poor man's relay. And, we already control the channel in other ways, when we decide where to install a base station, how much to down tilt the antennas, etc., etc. So there are ways in which we can control the channel to some extent. This is one more way, which has interesting aspects, mostly that it's passive. But I don't think you could run an IRS on batteries. So it's going to have to be plugged in anyway. And being passive is also a limitation, because then you're really going to have a huge number of elements, so reflecting units, if you want the impact to be substantial. So I think the jury is still out, and you guys have published some provocative papers on this, which I have right here on my desk. And I'm in a new European project devoted to this topic, so I'll be working on it. My impression is that these IRSs might make a bigger difference at very high frequencies, say millimeter wave or even sub-terahertz, where the omnidirectional path loss is awful and the wavelength is tiny. But then the challenge will be to have materials that can operate at these frequencies. So I think on this topic especially, working with people from industry who understand the hardware will be essential. Going back to our previous discussion on interaction with industry, yes.
Yeah, I think you're summarizing this well. I mean, for really high frequencies, we don't know yet, right? And reflecting surfaces could become an enabling technology there. For lower frequencies, it is nothing really more than a relay without amplification. And the question is then, why would you build a relay without amplification when you can build a relay with amplification, right? How about if we go to, a different topic here. So CDMA. Was CDMA just a detour in the history of wireless technology, or will it have a place, you think, in the future and in 6G in particular?
Yeah, CDMA is just not good for really broad bandwidths. There is this wonderful paper by Tarantse that showed beautifully how the uncertainty in the estimation of the multipath components keeps getting worse and worse as the bandwidth goes past a few tens of megahertz. And there's nothing that can be done about it. It just becomes impossible to lock with sufficient accuracy on those multipath components. And the receiver is fundamentally unable to capture most of the power that's coming in, right? So, but CDMA is good for things like random access, right? Say in control channels, for massive multiple access maybe. So there are niche applications. But as a main means of access, I think that its time is over. It brought with it some fantastic progress in signal processing and some lessons in system design. But it is inevitable, as you were hinting, to think that perhaps we could have gone straight from TDMA to OFDM, bypassing CDMA, right? For those who were there, this was, sorry to interrupt you. For those who were there, this was, when this was debated, it was an exciting and very intense time. I was a student at the time, and my advisor was a very vocal opponent of CDMA. So I lived that conflict from a close distance. Everyone had an opinion, discussions were endless. And on the technical merits, there wasn't a clear winner. So no one ever convinced anybody else that they were wrong. In reality, of course, the adoption of CDMA was driven by politics and intellectual property. And that's what carried the day.
It is indeed, to my understanding as well. And it seems that there was no fundamental reason for why we could not have built OFDM directly, right? Which is superior from so many perspectives. What do you think of multi-user detection? There used to be a mainstream research topics for CDMA, particularly something like 20 plus years ago, and which has also come back to some degree now with MIMO and going beyond, say, the simplest linear processing that massive MIMO typically builds upon. Will that have a place in 6G?
Yeah, I think that multi-user detection, it just has blended into everything we do, right? Even if the term itself has gone out of use. So multi-user MIMO can be seen as multi-user detection.
It is.
Even single-user MIMO, right? If you interpret each antenna as a user, right, is MUT. Cell cooperation also has MUT aspects. So anytime we work with vector channels, in a sense, we're doing a form of multi-user detection, right?
It is indeed. And I guess the point here is that with massive MIMO in particular, then the multi-user detection problem has become so much more well-conditioned that we don't need very advanced algorithms most of the time. How about NOMA? We touched upon that earlier. Do you think NOMA will be part of 6G or an important part of 6G?
Yeah, I think I already expressed my opinion about NOMA. I think the concept doesn't even make much sense if you think about it, because it's defined as the negation of something, right? So if we take the definition at face value, then anything not orthogonal is NOMA. So MU MIMO, for instance, would be NOMA, right? So it's a concept I'm not fond of. And anyway, the gains of NOMA are very small. We're talking 20 or 30% when the channel gains are very skewed. And nothing when the channel gains are balanced. So it's a lot of work for very little reward.
Yeah, you have to look very hard to find a case where NOMA actually brings any gain, right? I think we even talked about this on the podcast. And
yeah, we had an entire episode.
We did, yeah. Yeah, so I guess we're approaching the close-up here, but I'd like to hear your views on information theory as an academic discipline. What do you think are the most important breakthroughs that have been made in information theory in the last, say, 10 or 20 years? I mean, I tend to think that, for example, well, you know, all the theory behind massive MIMO, right? Well, that is applied information theory, but information theoretically speaking, it relies on rather simple techniques and capacity bounds there. So perhaps it is that the most important breakthrough that's been made is on short block length information theory. Do you agree with that? Or is there, or what are really, let's say, the three most important developments we've seen in that field?
I do agree. I think the discipline of information theory and the society itself had a bit of a crisis with many derivatives. And they've been doing some soul searching. But my impression is that they're bouncing back with new young people, a lot of talent. It's a small community, but talent is not something they've ever been short of. So they have this thing, right, that they have such a well-defined founding father in the iconic figure of Shannon, which is a blessing, but I think it's also an issue because of how they're beholden to this figure. But in terms of the contributions of recent years, I totally agree with you. I would say over the last decade, so Polar codes, maybe it's already been more than 10 years, but just about, right? Polar codes, and then all these results on short block length communication, definitely. And maybe, again, Poniansky, there's all this work on massive multiple access also, I think is rather interesting. And we'll have to see which ramifications it has over the years. But I think that it'd be great to see some new strong computer results emerging from information theory, and I'm staying tuned for that because it hasn't happened now for some time.
Yeah, so short block length information theory and then massive multiple access and unsourced random access. So you mentioned polar codes. How much better are polar codes quantitatively speaking than, let's say, LDPC codes for reasonably long blocks or classical convolutional codes or trellis-coded modulation for shorter blocks?
Yeah, I'm not a coding guy, but my impression is that the advantage is more on the implementation than on the performance. I would say they perform just about the same, but they're easier to implement.
Yeah.
Mostly, I think what's nice about them is it's a completely different way of doing coding, right? Completely unrelated to any other type of code done in the past, right? So that's very refreshing. And who knows, it could bring new things with it, right? This type of, polarizing the channel this way, we may see still new benefits from it.
So what do you think or is the most important problem that information theorists should tackle in the space of, say, communications and wireless communications in particular?
Yeah, I don't know. I'm a little off information theory in recent years. I've gone back to sort of hardcore communications. I still track what's going on there, and of course, as a tool for our work, it's extremely elegant, right? It's supremely elegant to use information theory. I think nothing compares to it in that sense. But the results we're using for our work, you guys and myself, are old results, right? I mean, we're using just classical mutual information expressions and the SAT. So it's become just something we have as a tool at our disposal. We use it, and we're not using anything that's been developed over the last 20 years, I would say. You don't need any of that for massive MIMO, right?
Yeah, it is a tool, although it's a highly foundational tool for all of us working on wireless problems and research. Yeah,
I have a last question, which sort of goes back to the thing. Okay, we are observing one generation happening every 10 years. So say that the sort of the research starts every 10 years at the beginning of the decade and it ends towards the end of it. And now we're only 1 year into the research into 60. And if you look back, you wrote this paper, what will 5G be in 2014, which was like 4 years, halfway almost through the 5G research time, when people at least started to have a sense of what 5G is going to be. And then now we can see that maybe due to the great success of that paper and many other papers, people try to write similar foundational papers, and you can probably find like 50 different 6G roadmap papers that people hope to gain the same kind of impact with. And so I'm witnessing this kind of tsunami of publications. And then I remember that you once told me that you had a different approach to publishing, that you rather try to publish less. So for the benefit of our listeners, could you just explain briefly how you are looking at the publication process?
Yeah, so in terms of the 5G vision papers, I remember maybe 2 years ago, I talked to some of the co-authors from our 5G papers, Stefano Buzzi, Jeff Andrews. We talked about, should we write a 6G vision paper? And we concluded we had no clue of what 6G would be, so we didn't know what to put in the paper, so we didn't write it. But other people have. Now, tsunami of publications, yes, you're absolutely right. So let me give you a data point, right? Right now, we're adding 1 million documents to explore every 3 years. 1 million documents. This is the amount that was published the first half century after Shannon, right? So the increase in publication is staggering. If I have a plot somewhere, exponential, right? Now let me ask you this. Do you think that the rate of new ideas is also growing exponentially? I think it isn't. Quite the opposite. So the mathematical conclusion is that the amount of new ideas per paper is going to zero. The vast majority of papers that are published these days are not even cited, maybe not even read. So this is a concern, and maybe we have to devote a whole episode of Wireless Future to this, because I think we already consumed all our time today, and this topic is very important to me. So it deserves maybe another separate discussion one of these days.
Yeah, I think what you said here really resonates with probably both of us, Emil.
Yeah, I think you mentioned that you sometimes look back at what paper you have written yourself and think about how to publish less as well. Is that right?
Yeah. So you're right. Every few years, I go through this exercise of looking back at my papers and seeing which ones I wish I hadn't published. And it's a sobering exercise that I recommend to everyone, because then it makes you think before you submit a new paper as to whether in a few years you're going to regret having submitted this particular paper. So I totally recommend it.
Yeah, I think this is a great point, and that particularly for people who want to be active in this field for a long time, to try to make their names associated with a few good papers rather than having a huge amount of publications that I mean, you want people to see your name and think that this is a paper that you would like to read among the exponentially increasing number of other papers that are appearing.
All right, so with those final insights, perhaps we are approaching the close-up here. So this has been great fun and educational. Thanks a lot, Angel, for being with us today. Thanks, Emil. And thanks to our listeners. Bye-bye.
Bye-bye.
Bye-bye.